Hi, good afternoon, everybody. My name is Yaron Bromberg from the Hebrew University, and I'd like to start by thanking the organizers for putting together this really exciting meeting and for the invitation to present our work on shaping light in multimode fibers. In the past few years, multimode fibers have been raising lots of interest in a wide range of application of optical disciplines, ranging from basic research on random medium, quantum, and nonlinear optics, to technologies such as spatial division, multiplexing in multimode fiber communication, and endoscopic imaging. Now, in fact, multimode fibers are with us for a very long time. And for example, the idea of transmitting images through optical fibers for endoscopic applications dates back to the 1930s when Heinrich Lamm managed to image a filament of a light bulb through a bundle of optical fibers in this remarkable demonstration. So if we ask ourselves, what is the reason for the tremendous amount of interest in multimode fibers over the past few years? The answer, I believe, is that we live in the digital age of multimode fibers. Today, we have phenomenal technologies to precisely structure the light coupled into the fiber, allowing us to synthesize modes of the light excited in the fiber. And in addition, the ever-growing computational power that we have in our favor allows us to apply advanced digital processing to images recorded at the output of the fiber. So we have powerful computers that can precisely control the incident light and process the recorded images. And it's this ability that has opened many new opportunities for using multimode fibers. Today, I want to tell you about our work on developing a new way to synthesize the light propagating in multimode fibers. And the question we asked ourselves is whether we can control the light, can we shape the light at the output of the fiber without using a spatial light modulator in the input. We want to somehow directly manipulate the light inside the fiber in order to get a desired pattern at its output, again, without any SLM at the input. One motivation for such an all-fiber SLM, or all-fiber light modulator, is to shape the light that is generated inside the fiber itself. In my lab, we work a lot on generating pairs of entangled photons inside multimode fibers using the process of spontaneous four-wave mixing. So we come in with a strong green laser, a green pump laser, and by the four-wave mixing process, two green pump photons are annihilated in the fiber, and a blue and red photons are generated, where due to phase matching, the idler photon, the red photon, is, in this example, generated in a high order mode, whereas the signal photon, the blue photon, is generated in the fundamental mode. Now, in many quantum protocols, we need to control the shape of the photons. And since they're already inside the fiber, we don't want to couple the light out of the fiber, put an SLM and couple them back in. We want to do the entire synthesis, to synthesize the shape, to do everything inside the fiber. Now, these images we're taking in a high flux regime, so we can get nice RGB images, but in reality, when we work with single photons, we dial down the power of the pump. We have a really weak flux of pairs of entangled photons, so it's very important for us not to have to lose more light and coupling in and out of the fiber. So this is a motivation, but I should say and emphasize that everything I'm going to show you today will be with classical light. So the quantum part was more of a motivation, but everything, all the results I'm going to show you will be with speckle light. Now, with the laser light, sorry. Now, how can we control? So going back to our goal of controlling the light at the output of the fiber by manipulating the fiber itself, the way we do it is that we know that when we couple a laser light into the fiber, we get at the output speckles due to model interference. Now we know that every tiny perturbation, any tiny mechanical perturbation to the fiber, even a slight touch, completely changes the speckle pattern that we see at the output. So here in this illustration, we see 3 different configurations of the fiber generating 3 different speckles at the output. Now, usually this sensitivity is a bug, right? It's annoying to work like this with fibers, but in this work, we want to use this bug as a feature. How can we use this? By simply using computer-controlled deformations at multiple points along the fiber. So how do we do it? Here is how we do it. We take a multimode fiber and we couple a Heaney laser into it. So this is the red light that you see. And now we place along the fiber 40 computer-controlled piezoelectric actuators that apply local bends along the fiber. Our colleagues call this configuration the fiber piano. And if we zoom on one of the keys of the piano, okay, one of these piezos, if we zoom in, we see here the piezoelectric bender. It can go up and down and travel of a few hundred microns. And as it goes up and down, it bends the fiber, introduces some stress, and the stress introduces a mode-dependent phase, and the mode-dependent phase changes the structure of the speckle pattern at the output. So we couple light into the fiber, and the coupling is fixed. We don't have any SLM here, so the input is fixed. And now, just by moving the piezos, we can change the pattern that we record on the CCD camera. So how can we use this as a modulator, as a light modulator? We use some kind of iterative optimization algorithm and set a target. We want to get some target pattern at the output. We run the optimization algorithm. So you can see here that applies different voltages to the piezos, and it's a little bit hard to see in this video, but the piezos are moving up and down. The images are recorded and processed by the computer, and the optimization algorithm searches for the voltages we need to send to the piezos to get the desired output. Now, it doesn't really matter. We use in this example the particle swarm optimization algorithm, but basically any iterative algorithm we've tried work. It could be genetic algorithm, it could be stochastic gradient descent. They all work more or less with the same efficiency once you tweak the parameters of each algorithm. So we wanted to test this idea, first on focusing the light to one spot at the output facet of the fiber. The algorithm looks for the voltages that will maximize the intensity in some region in some spot that we choose on the camera, and try to maximize the intensity on that spot. On the left, you can see the speckle pattern before the optimization. And on the right, you can see the pattern we get after the optimization, where most of the light is concentrated on the spot here. And we can define the enhancement factor, being the intensity at our target area relative to the average intensity. And in this example, the enhancement factor we obtain is 25. Now, the enhancement factor depends on the number of actuators we use. Obviously, the more degrees of control we have, the more piezos we have, the larger the enhancement, right? We have more control. What's interesting is that the scaling of the enhancement factor is linear in the number of actuators. While for spatial light modulators, it is well known that the enhancement scales linearly with the number of SLM pixels, here the linear scaling is a little bit less obvious, because unlike spatial light modulator pixels, here the actuators, the piezos, the degrees of control affect each other. They're not uncorrelated. For example, if you move the first piezo in the array, the distribution of the light inside the fiber changes, and hence, the way the light interacts with all the other piezos also changes. Nevertheless, as we see here, we get a nice linear scaling with a slope of 0.7, which is quite high, actually. It's very close to the values people observe with spatial light modulators. Okay, next, we tried another task. Instead of focusing the light at the output facet of the fiber, we wanted to demonstrate mode conversion in a few mode fiber. So we took a fiber with a smaller core than before. Here it's just a core diameter of 10 microns and an NA of 0.1. So the fiber supports just a few modes. And on the left, you can see the result of one optimization that we ran, where we tried. Okay, we started with a state. These are images of the output before and after the optimization. So before the optimization, we start in a situation where we have in the horizontally polarized light a TE mode and nothing in the vertically polarized light. And we set a target. We wanted to get at the output a fundamental mode in the horizontally polarized light and a TE mode for the vertically polarized light. So this is our target. We run the optimization, and this is what we get after the optimization. So you see a very nice correspondence between the target and what we get. The Pearson correlation between these two targets is 0.92. Now, in this example, we use 33 actuators. We wanted to see what happens if we use less actuators, because essentially it's a few mode fiber. It just supports 3 modes per polarization. And we see that even just with 12 actuators, we can still get a nice result. So we start with some mixture of H and V polarized light. We wanted to get here just horizontally polarized light in TE mode. And after the optimization, we get something that is very close with a Pearson correlation of 0.9. Now, I should mention that, like the time it takes to run this optimization, like in the last example of the few mode fiber, is about 10 to 15 minutes per run. Now, in principle, what limits how fast we can go in our mechanical implementation is the response time of the system to mechanical perturbations, which we could measure by just taking a subset of the piezos, abruptly change the voltage across them, and measure the correlation between the speckle pattern before we made the voltage change and after. So we can see a very sharp decrease in the correlation right after we apply the voltages. And then the time scale, if we zoom in over this fall, we can identify that the time scale, the time it takes for the pattern to change it significantly is something like 30 milliseconds. It's more or less the same time scale if we change 1, 2, 5, or all the piezos. So basically, this 30 millisecond time scale sets a maximum on the modulation rates we could achieve, which is 30 hertz. That's comparable to spatial light modulators. In practice, we use far less a lower rate, something like 5 hertz. And this is because of electronic latency. And definitely the electronic circuits we use was not optimized at all. And we believe essentially it is possible to achieve a 30 hertz modulation rate. Now, before we carry on, let me mention another advantage of the fiber piano configuration beyond it simply being an all-fiber configuration. Now, let's for a second look at the standard way of wavefront shaping in fibers, where you put a spatial light modulator before the fiber. And what you do is you control the input and look at the output. What's important to note is it doesn't matter how many pixels. If you have lots of pixels on the spatial light modulator, essentially what the SLM does is controlling the amplitudes of the different fiber modes. So if my fiber supports N modes, I can describe the propagation in the fiber by N by N transmission matrix. And then what the SLM does is controlling the weights or the amplitudes of the different modes. So that's like N complex numbers or 2N real parameters that we can control. Now, in contrast, in our piano configuration, what we do, the input is fixed, okay? And by pressing the point along the fiber, what we are actually changing is the transmission matrix of the fiber. But the transmission matrix of a fiber has N square degrees of control. So in principle, we are not, the number of degrees of control we have in the system is no longer limited by N, by the number of guided modes. It's actually limited by N square, the number of elements in the transmission matrix. And this is for monochromatic light. In fact, if we have several spectral channels, it will be N square parameters for each spectral channel. This is very nice because basically this approach can open the door for really engineering the transmission matrix of the fiber and not just the input. Now, one might ask, why would we want to have more degrees of control than the number of guided modes in the fiber? And the answer is that when you can control, in this way, by controlling actually the transmission matrix of the fiber, you can control the output for multiple different inputs simultaneously. And in that sense, we can turn the fiber piano to a reconfigurable multiport interferometers. Now, in recent years, there are several exciting platforms for multiport interferometers. And here are a few examples. For example, you can use many phase plates placed at different planes through which the light propagates to convert, to make a multiport interferometer. You could use a spatial light modulator and bounce the light multiple times off the modulator, each time applying a different phase mask. It's also been demonstrated, like multiple port transformation has also been demonstrated in a mesh of integrated Mach-Zehnder interferometers on chip, and also in a more amorphous structures in silicon. And essentially what's nice with the fiber piano is that it has the potential of controlling the full transmission matrix. And it's simple. It doesn't require any special integration, fabrication, or alignment. But of course, there's no free lunch. And the price we have to pay for this simplicity is that we'll have to, if we really want to design a transmission matrix, we'll have to use an adaptive optimization in order to get the desired matrix. So this is more of an outlook, and this is one of the things we're currently working on now with the piano. Now I want to shift gears and tell you about another application we're using with the fiber piano, and that is to train neural networks to learn the transmissions for multimode fibers. Now, about 2 years ago, in 2018, the teams of Moser and Psaltis from EPFL have shown that it is possible to train a deep neural network to learn the input-output relations in multimode fibers. And that's in order to reconstruct from the output speckle patterns the images that were transmitted through the fiber. What typically people do is use a DMD to project some digits or letters on the input facet of the fiber. At the output, the intensity speckle patterns are recorded. And using a trained neural network, the digits or whatever the object was are reconstructed. Essentially, what the network does is it learns the transmission matrix of the fiber, but using only intensity measurements. Usually, for the transmission, to learn the transmission matrix, we need to measure the fields, the complex fields at the output. But here, thanks to the neural network, it's possible to reconstruct the inputs simply by intensity patterns. So this works very nicely. The problem is that the input-output relations are very sensitive to perturbations of the fiber. So if the fiber moves a little bit, and the network needs to be trained again. This problem, the problem of the sensitivity was addressed in this recent work by the team from Queens College, where the network was first trained on a static fiber. So here is the ground truth, the object that was sent through the fiber, and the network was nicely able to reconstruct them. And this was for a static fiber. And then they applied something in the fiber moved. In this example, they took a metal rod and moved it by a few centimeters and changed the bend here of the fiber. And when they tried to reconstruct the images after the fiber has moved, the network didn't work well. What they did next, and now they trained it again, they moved the rod over several different positions, trained the network over all the positions of the 6 configurations in this example, and then the network was able to reconstruct quite well the objects. The problem with this approach is that with a moving rod, it's quite difficult to train the network over multiple different configurations, multiple different perturbations. And this is what we'd like to do if we want to make a network that is resilient or at least less sensitive to mechanical perturbations. But with our fiber piano, it's quite easy to make many different configuration, many different deformations to the fiber quite quickly. And then we can train the network over all these deformations. So the network, the convolutional neural network that we use had a unit architecture. Basically, it starts with taking the images we record on the camera, the images we send to the fiber, which are 128 by 128 pixels, and then it contracts and takes smaller and smaller layers, but deeper, so less pixel, but more channels, and then it expands again. So this architecture of contraction and expansion is the unit architecture, and we use this this network with something like 2 million learnable parameters to learn the transmission of our fiber for different fiber piano configurations. So first we started with one fiber configuration. So we just sent some random set of voltages to the fiber piano and keep it fixed. And then over this one fixed configuration, train the network with something like 60,000 inputs. We record 60,000 speckle images. Send it in, use those input-output pairs to train our network. And then to test the network, we send a new set of objects, a new set of images that were not used, of course, in the training session, and try to, from the speckle patterns we measure for this new set, try to reconstruct the digits at the output. Now, again, this was, and so far, everything is done for a single fiber configuration. Nothing moves yet. And when we do it like this, but essentially we get the similar results to the 2018 papers, where for the single configuration, we are able to reconstruct quite well our object. So you can visually see a nice matching between the digits and the ground truth, the object that we were sent. The pixel accuracy is very high, over 97%. And the classification error, what we did, after we reconstructed the digit, we used another network to classify the digits into the 0 to 9 digits and see if it classified it well. So we get very low classification errors, less than 4%. Now, this was all for a single fiber configuration. Next, we trained, because we have the piano and we can easily change configurations with it, we trained the network on 890 different configurations. That means 890 different sets of voltages that are sent to the piezo, and something like 800 images per configuration. Now, to test so we train the network, and then to test again, we send a new set of objects that were not seen by the network in the training session, but we sent them, the fiber was in the same configuration, 890 configurations that was used in the training. So the test was not seen, but the fiber configuration was the same configurations used in the training. And when we do it like this, again, this is the ground truth, the bottom row, and the middle row is the reconstructed images. And you see, it's not as good as before, because now I had 890 configurations, but the pixel accuracy is quite large, over 90%. The classification error is now between 20 and 30%, and that's mainly due to digits that are similar to each other. For example, over here, this 4 was the classification network identified this 4 as a 9. So whenever the digits are close, two digits are close, like a 4 and a 9, we got an error. Okay, the next thing we wanted to do is something even more ambitious. We wanted to train the network on some set of configurations, but then remember, our goal is eventually to train a network that is resilient to fiber perturbation. So when we test the network, we also need to change the fiber configuration if we want to really test if it really is resilient to perturbations. So we trained on something like 300 configurations, and then for the test, we used the new configurations that were not seen in the training session. Now, as a first step, we first tried, I say different configurations, but how different? Pretty obvious that if they're completely different, if there's no correlation between the configurations used in the training and the test session, the network doesn't have a chance to succeed. But if there is some correlation, and in the first example, quite a high correlation, so we quantify it by 0.8. What's the Pearson correlation of 0.8? We take the same input at the different configurations and look at the correlation of the speckle patterns at the output for a fixed input. And we tune the voltage change in the piezos so that the correlation for a fixed input, different configurations, will be 0.8. And now we use these kinds of sets of configurations for the training and a different set for the testing. And when we do this, and this is what again, middle row is the reconstructed digits, bottom row is the ground truth, is the objects, and we get an excellent correspondence. Again, very high pixel accuracies, over 97%, and classification errors of less than 3%. And this is quite remarkable. I remind you, the test was on a configuration, on bends on the fiber that were not learned by the network. However, the bends were, the difference in the bends was not so high. Like I said, the Pearson correlation between the different correlations was 0.8. Now, and obviously, we achieved these high correspondence, or the lower classification errors because of this high Pearson correlation. But we can make the larger voltage changes between different configurations. So we repeat the same experiment, now making big changes in the voltages, so that the Pearson correlation between different correlation drops down to 0.1. And now we see that the reconstructed images are not as good as before, but still, it reconstructs quite nicely most of the digits. We have a classification error of between 30 to 40%, but still pixel accuracy of more than 90%. And again, whenever the digits are close, like the 3 and the 5 here, then the classification network had a hard time to distinguish between them. But in many other cases, even though again, this is for testing on a configuration and bending the fiber in a way that was not bent during the training session. And we are actually quite happy with these high parameters. Okay, I think I've used most of all of the time, so I'll briefly conclude and say that I hope I convince you that with the Fiber Piano is an interesting platform, both as an all-fiber SLM, a way to shape the light, and also to train neural networks. Currently, we're working on extending these ideas to control also the polarization and the spectrum of the light, and also controlling nonlinear processes in the fiber. And before I end, let me thank really the wonderful team that worked with me on these projects. The people in bold are those who contributed to this presentation, but it's mainly the work of Shachar Sisi, really a brilliant student who took the lead on this project. And let me also thank our collaborators, Daniel and Jonathan, and especially Sebastian Popov, who will be also giving a talk later on during this panel. So thank you all for your attention, and I look forward for your questions in the Q&A panel.